Hi guys, welcome to our second field presentation on ADSL technology. We are going deeper and we are going to have a look at frequency division multiplexing with reference to the bandwidth of the UTP cable. We are also going to have a look at how to connect a business customer and also how to connect a residential customer. We are not going to leave the faults or the payments that affect ADSL, like attenuation, how it affects ADSL, split pair, bunched pair, corroded or loose joints, and skin effect. As usual, Motion Marfus is my name, and for any communication, motionmarfus68@gmail.com. You can also come via WhatsApp +263 7758 Enjoy. These are our objectives in video presentation number 2, and we are going to look at frequency division multiplexing of a UTP line, the communication system model in general, the Shannon-Hartree law and its effect on the capacity of the UTP cable, how to connect a residential and business customer onto an ADSL network. We are also going to have a look at AAA server and DSLAM as network devices. Then we are going to explore UTP channel impairments, where we'll be looking at signal attenuation, bunched pair, twist split pair, corroded or loose joints, skin effect and its effect, and the effect of these on ADSL speed. Let's enjoy. Frequency division multiplexing, in short FDM. What we do when we are subdividing a given frequency band into distinct bands. Like in this case, the bandwidth of the UTP line is 1.104 megahertz. So we are subdividing it into distinct frequency bands so that each band is used to carry a certain frequency range of signals. So we are saying the twisted pair can be split into the following frequency bands or channels. And the channels are used to carry voice, video, and data. So we have divided this frequency band from 0 up to 1.104 megahertz into 1, 2, 3, 4 bands. The 0 to 4 bands we are calling it the PSTN. Then from 4 kHz to 25.875 kHz, or roughly to 26 kHz, is the guard band. Then the upstream from the customer's premises to the exchange is from this range to this range. Then from this range to this range is the downstream. If you can see, this is the widest. In other words, this is the fastest, followed by this. This is the slowest. This is where we have dial-up or voice band modem. This is the guard band. It is used to separate low frequency signals, voice, and high frequencies ADSL signals. Hence Fig 1.1 shows the ADSL frequency spectrum. An explanation of FDM or frequency division multiplexing. We have said the PSTN of voice covers the frequency range 0 to 4, and this carries voice and is the slowest speed. The guard band separates voice and data and does not carry anything, and this is the frequency range. The upstream from the customer to the exchange is from this range to this range, and it carries data from the subscriber to the exchange. Then the downstream from 138 kHz to 1104 kHz, it has got the highest bit rate and carries data from the exchange to the subscriber. The wider bandwidth is the reason. Please take note, this is a very important point. Some people were asking why the downstream speed is higher than the upstream speed. This is because the bandwidth is wider. So, hence this statement. The wider bandwidth is the reason why downstream speed is far much higher than the upstream speed. Then a question. Convert the above frequency, the frequency range is 2 megahertz. You convert this 4 kilohertz to megahertz, so it will be 0 up to you simply divide this by convert this to megahertz from there to there, from there to there. This is for you. So we are saying the wider frequency range, the faster the channel can carry data, or the more data the channel can carry. Highest frequency minus lowest frequency gives us the bandwidth of a particular channel. Take note of the frequency ranges and or the various bands and what they are used for. A typical ADSL connection for a residential customer. As you can see, we've got a splitter. This is a UTP line. All connections are done at the MDF. So we've got some wires from there to the DSLAM and the line that goes from the customer. It is also terminated on the main distribution frame. So when we get to the customer's place, we terminate the line onto our ADSL splitter. It is one incoming, two outgoing like this, and they are labeled ADSL modem and telephone. Then from the ADSL modem port, we are going to connect our ADSL modem. Then this modem is going to be connected to the PC or to our laptop using RJ45 patch cable. Then from the phone port, we are also going to connect our analog telephone line. Then also from the same main distribution frame, we are going to have some jumper wires that are going to connect to various modems inside this DSLAM. Then from the DSLAM to the MPLS cloud, then from there to our internet. So this is a typical connection of a residential customer. This is simply an explanation of the previous slide. And let me rush through it. We are saying our modem needs power for it to operate, and it must be connected to the splitter modem port, and the type of cable using is called RJ11, and RJ stands for registered jack, or it is also known as a telephone cable. It's the same cable that is used to connect, where we connect our analog telephone lines. Here is an important point. If you mistakenly connect the ADSL modem to the telephone port, the link or the ADSL light keeps on flashing, resulting in no internet access. In other words, it will not sync. The two modems will not sync. They will not turn hard on. The reason is the port blocks ADSL signals. Why? Because of the low pass filter. Where do we connect the analog telephone line? It is connected to the splitter telephone port, which means the port is labeled such. And if you mistakenly connect it to the modem port, you get the dial tone, but there will be some background noise due to high frequency ADSL signals. And hence what I've been singing about. This proves that the high pass filter is not in the splitter but in the ADSL modem, ATU. So we are saying the splitter is connected to the telephone line RJ11 socket, and from the socket to the main distribution frame or to the UTP line, and then from there to the DSLAM, to the MPLS cloud, and to the internet. Figure 1.3 shows how a business customer can be connected onto an ADSL network. How does it differ from the previous slide of a residential customer connection? We have added a switch, and these switches allowed us to connect client A, client B, client C, and we have also added this proxy server with one network interface card. So this switch is connected directly to an ADSL modem using a cable, an RJ45 patch cable. RJ stands for registered jack. The connection to the internet cloud remains the same, and also from the main distribution frame. A brief explanation of the connection of a business customer onto an ADSL network, and we are saying the switch has been added and is connected to the ADSL modem, as I said, using an RJ45 patch cable. No configurations are required for such a connection, and we are saying a proxy server to allow controlled internet access is connected to switch to which all other devices that need access to is connected. You know what? This a proxy server enables us to use a private IP address in our network. So all requests, HTTP requests, they don't go straight to the internet cloud. the requests are made to this end, if it has got a cache of some pages, it will simply respond. If it doesn't, it is the one that goes onto the internet to request those pages. So the HTTP requests and replies onto the internet are made by this. And if it has got some caches of those requests, it is the one that responds and supplies the replies to the customers that would have requested. So by so doing, it increases the speed of the network. Another look at another ADSL network devices, this time AAA server. This AAA is short for Authentication, Authorization and Accounting. Strictly speaking, this is not an ADSL network device. The typical ADSL network device is a BRAS, standing for Broadband Remote Access Server. But this device is not able to carry out these AAA functions, and this server is brought onto an ADSL network so that it is able to authenticate, authorize, and to account. Let's look at each of these in detail. Authentication, we know this from our PCs or from our laptops or even from our smartphones. It determines who the user is and whether the user should be granted access onto the network. So we want to prevent some intruders onto our network. So we use ADSL passwords and username databases. All these are stored in the AAA server. If you wrongly configure an ADSL modem with a wrong username and password, this device will not allow internet access to such wrongly configured ADSL modems. What we mean by authorization? This determines what the user is allowed to do. So, by so doing, it allows network managers to limit network services to users. Then the last A, accounting. What all the user does on the network is accounted for. So this happens because we track what the user did and when he did it. In case the user can deny that he or she did not do anything on our ADSL network, we can prove this using the AAA server by tracking what you would have done and when you would have done it. More on AAA server. So we are saying the central management that is done by the AAA server ensures that information is in a single centralized and secure database that is easier to administer. So we are saying, please take note of this important point. We are saying on an ADSL network, the username and password that are created and configured in the AAA server, they must match the username and password that are configured in the ADSL modem, or else the ADSL modem is denied internet access by the AAA server. This is an important point. Never reset an ADSL modem unless you know the correct username and password, or else you leave customers with no internet. So what we are saying is, in the DSLAM, this is not where the username and password are configured. They are configured in the AAA server. This is a picture of a DSLAM. DSLAM, I said it stands for Digital Subscriber Line Access Multiplexer. On this, we've got various cards. All these are cards. If the card develops a fault, you simply remove it and you replace it with a functioning card. You find control cards, and you also find some cards where customers are wired or where customers are connected. And for example, I know of Alcatel's cards when 48 customers can be connected. So on that card, That's where the number of a particular customer is labeled. The port is unlocked to establish a connection between a remote ADSL modem and the modem on this particular card. So this is just a picture of an ADSL modem containing various cards responsible for different functions. In more detail, a DSLAM, it is located at the central office or at the exchange. And what does it contain? It contains ADSL cards that contain bank of modems and splitters, which means on the particular printed circuit board or the card, as we are referring it to as, that's where we find modems and splitters. They are not standalones. Please take note. For example, each card can contain 50 ports for modems, which is very important for port counting at the main distribution frame. But of these 50, we only use 48 ports. And please take note that port 25 and port 50 are not wired, which means they are left idle. And take note that each modem and filter in the DSLAM is connected back to back with those at the subscriber's premises. So we are saying modems that are in the DSLAM are on the cards, and we know that from our previous presentation they are known as ATUCs. Those at the subscribers' premises are known as ATUR. So we are saying a DSLAM is the interface between all customers and the switch. It does the multiplexing of data to the backbone and demultiplexing of data from the backbone. So we are saying a DSLAM contains other cards apart from the ADSL cards, like the control cards that control the whole shelf. And if anything goes wrong, we'll see some alarms. This slide, guys, is very, very important, and it's a generic one. It's found in telecommunication, it's found in communication in general, that we have got a source of information and we've got a destination of information. We have got a transmitter and we ought to have a receiver. And we've got the means that is going to carry our signal from the transmitter to a receiver, and we are calling it our channel. Although for communication to be effective, it must be two-way. We are only representing one way in this case, from the information source to the destination, from the transmitter to the receiver, through our channel. Channel can be A, channel can be UTP, channel can be optic fiber bar, channel can be radio waves, etc., etc. So we are saying our information from the source, it must be sent to the transmitter, where it is going to be adapted to the characteristic of the channel, so that it is able to propagate effectively from the transmitter to the receiver by modulation, by amplifying. This information source can be a computer, it can be a microphone, then our transmitter. In face-to-face communication, this can be a human being. So our channel can be air there. But in our case, this can be a computer. This can be a computer, it can be a smartphone. Then this information must be sent to the transmitter, our ADSL modem, from there to our channel, which is UTP, to a remote, in our case, to the DSLAM, then from the DSLAM to the internet. But take note of this guy. This is our enemy. Noise gets into the communication system through the channel, and our channel is UTP. If we didn't have this guy, then our communication was going to be effective. So noise tends to perturb the proper reception of information as it propagates from the transmitter to the receiver. So we are saying most of the noise that affects the wanted signal is external noise, and it enters through the channel or the transmission channel that is through our UTP line in this case. Shannon-Hartley law, these are two guys, Shannon and Hartley. This is important. This is important, guys, for ADSL technicians or for an ADSL or customer to understand. So we are saying the theoretical maximum data transfer rate of a transmission line can be calculated using this equation. We call it Shannon-Hartley law. It says that the capacity of a channel C is equal to the bandwidth of the channel B multiplied by log to base 2 of, in brackets, 1 plus signal to noise ratio. This S stands for signal and this N stands for noise. What is our C? C is the capacity of a channel in bits per second. So our channel in this case is UTP, where bandwidth is B in hertz and S is the signal power, which is our ADSL signal in watts, and our NME N is noise power in watts. Guys, from mathematics, if this increases, this ratio is going to decrease, and if this decreases, it means what is now left in the brackets to base 2 approaches, for example, 0. This means that our C is going to approach 0 since we are multiplying this by this to the base 2. So we are saying, let's have a look at the explanation there. We are saying it is clear that if we increase B, and also increase signal to noise ratio, it means that our data rate C is going to increase. How do you increase S over N signal to noise ratio? We simply decrease noise. If the denominator becomes small, this ratio becomes high. If the denominator becomes high, this ratio becomes low. So if noise increases on our UTP line, this is going to decrease this ratio. So we are saying in practice, the data rates achieved are much less. This C normally decreases due to extended length of the line, due to crosstalk, and also due to noise in general. Guys, what we mean? We are saying for us to have reliable transmission between the transmitter and the receiver, the capacity of our UTP line, which is C, must not be exceeded. So we are saying the data rate at which we can send data along our UTP line must be less than the capacity of that particular UTP line, which is C. So a report can be made so that the line is attended to based on the figures observed as the line gets worse and never better on its own. We are saying if there is noise on our line, if this signal to noise ratio is low, you must make sure that you report so that your line is attended to. It does not get better on its own, but instead it gets worse. We are going to have a look at it when we do the modem configurations. On Shannon-Hartley law, we are saying when we turn on our modem, the modem is going to measure the signal to noise ratio on our channel, the attenuation on our channel, the downstream and the upstream speeds as well. And we are saying if the signal to noise ratio is very low, our capacity, the capacity of our channel will not be able to carry any ADSL signal, and the ADSL link light continue flick to go on and off. Please also take note that attenuation on our line, it must not exceed 60 dBs. If it exceeds these 60 dBs, the two ADSL modems or the two TUCs won't synchronize. The link won't come up. While our signal to noise ratio, it must not be below 7 dBs. dBs are units used to measure gain or loss. So we are saying for signal to noise ratio, the higher the better. For attenuation, the lower the better. Please take note, these are very, very important. So any signal, whenever our signal to noise ratio goes below 7 dBs, our link or our ADSL link light goes off. And once that happens, internet light turns off, meaning you won't be able to access the internet. So we are saying anyone, even the customer, can access the ADSL modem and check attenuation and signal to noise ratio on his or on her own. And these results, they show the quality of a line. So a customer can get into his or her modems, check attenuation on his or her line, and also check the signal to noise ratio. And he or she can make a report on his or on her own. Please, customers, take note that when your line has been attended to by telecommunication technician, you can, after they would have left or while they are still at your place, you can go into the modem and check these parameters, the attenuation and the signal to noise ratio. And if they are nearer this ratio or nearer this loss, you can advise them to work on the line, since this must be very high and this must be very low. To work examples on Shannon-Hartley law, we are saying if we've got a very high noise on our channel, it means that our signal to noise ratio is going to approach 0. And if this approaches 0, it means that C is going to be bandwidth multiplied by log 1 to base 2. If you solve this log 1 to base 2, it is going to give you a 0. And this bandwidth multiplied by 0 is going to give you a 0. And what does the 0 mean? It means that the capacity of our UTP line is 0, regardless of our bandwidth. So in other words, our UTP line won't be able to carry our data. Let's go to another worked example. We are saying we can calculate the theoretical highest bit rate of our regular telephone line. Let's take note. A telephone line has got a bandwidth of 3000 Hz. That is, it has got its frequency range is from 300 to 3300 Hz. So the signal to noise ratio is usually, this is given, is 3162. Let's find our speed. Guys, take note that this is for voice band modem. This is for dial-up. Let's multiply. Our bandwidth 300. Our signal to noise ratio 3162. So this is going to, if we solve, please take note we've got a base 2. We must do what we call change of base. You change this to base 10. If you change this to base 10, it's going to be 3000 Hz multiplied by 11.62. So your theoretical highest bit rate for a regular telephone line is 34.860 kilobits per second. This is for voice band mode. For your practice, I've got 2 problems for you, number 1 and number 2. Go through them and you must be able to find the correct solutions. What was the capacity of this channel if the signal to noise ratio is this and also is this? The capacity of the channel when the signal to noise ratio is higher than when the signal to noise ratio is lower. And also we want to calculate the maximum bit rate for Wi-Fi transmission if noise power is equal to this. Try, guys. If you find any challenges, you know my email and my WhatsApp number. The performance of a network depends on bandwidth. There is an important point I want you to appreciate on this one. We have got bandwidth in hertz and bandwidth in bits per second. So this bandwidth in hertz is highest frequency minus the lowest frequency. And when it is wider, the higher the bits that can be transmitted per second. For example, we saw that the voice channel has got the least speed, or the PSTN channel has got the least speed because of its lower bandwidth. And the downstream has got the highest speed because of its higher bandwidth. So That bandwidth is found from subtracting the highest frequency from the lowest frequency. This bandwidth in data communication is the number of bits that can be transmitted per second. For example, one can say that the bandwidth of fast Ethernet FE is a maximum of 400 megabits per second. What does that mean? This means that the network can send data at 100 megabits per second. So basically there's a relationship between the bandwidth in hertz and the bandwidth in bits per second. An increase in bandwidth in hertz means an increase in bandwidth in bits per second. An increase in bandwidth in hertz means an increase in bandwidth in bits per second, which means that a wider bandwidth allows us to transmit data at high speeds. The relationship depends on whether we have baseband transmission or transmission with modulation, which we call broadband. We will not get into detail with baseband transmission or broadband transmission, but please take note of the relationship between the two. We are now going to look at faults that can occur on a UTP line. So we are saying, although faults can be due to misconfigurations in the ADSL modem, AAA server or DSLAM, the twisted pair faults can negatively affect the way our ADSL operates. This is because our twisted pair was originally designed to carry voice signals alone, but our digital subscriber line, it now requires us to carry 1,000 more times. So we are saying these channel imperfections for voice can be devastating for our ADSL signal. Several times I've attended to faults where voice was working well while ADSL signal was malfunctioning. So we are now going to look at these UTP channel impairments. That is, faults that affect ADSL but don't affect voice. And these are signal attenuation, which is loss, corroded and loose joints. This is an enemy of ADSL. Water intrusion into our joints or into our UTP cable. Split pair and punched pair. We are going to look at each in more detail and how it affects ADSL. The first channel impairment that we are going to discuss is called signal attenuation. Attenuation is the loss of signal power as the signal propagates in a particular medium, and this is due to the physical resistance and also to the length of the line. So the physical resistance and the length of line results in loss in signal power or in signal strength. The amount of attenuation depends on frequency of the signal. One, it also depends on the length of the line, and it also depends on the material used to make up the particular medium. The unit of signal attenuation is decibels. So the longer the UTP line, the more the losses. The higher the frequency, the more the losses. Please take note. Normally there's nothing that you can do about signal attenuation except to reduce the length of the particular medium. Right? Another impairment, another UTP impairment is called a split pair. What is a split pair? Let's say you've got two pairs and a technician swaps the legs of the two pairs. That is what we call a split pair. So it occurs when a technician causes one leg of one pair to be caused with another leg of an adjacent pair. Although the metallic connection of the circuit is made, but what we know is that each of the two wires constituting the access network belongs to different individual pairs. By so doing, we have untwisted the two wires, and if the wire becomes untwisted, which means magnetic field around each wire is not going to be, the magnetic field of the two wires are not going to cancel. Hence, if it does not cancel, it means it is going to affect the current flowing in another wire, because the idea of twisting the two wires is to make sure the magnetic field of the two wires cancel. And we know that if there is induction of a magnetic field, the amount of current flowing in the wire is going to change. So a split pair works well for voice. but it does not work well for ADSL.
Another impairment or another fault that affects ADSL is called bunched pair. And what do we mean by a bunched pair? We are saying we can have two twisted pairs being wired in parallel at the exchange and also at the remote end, especially in the distribution box or at the cabinet, forming one circuit. The advantage of this is loop resistance is reduced, normally by half, and this happens is an advantage at low frequencies or at voice frequencies. At ADSL frequencies, it does not reduce loss, but here is what happens. We've got what we call impedance matching and impedance mismatching. Maximum power is transferred from one end to another end when there is impedance matching. So we are saying because we've bunched the pairs and we've reduced the resistance of the circuit, it means that we now have impedance mismatch, and when we have impedance mismatch, we don't have maximum power transfer. And when we don't have maximum power transfer, it means we've got some losses. So we are saying bunching of pairs impairs the impedance between the line and the ADSL equipment, showing that most of the power that was supposed to be absorbed by the ADSL equipment is reflected back towards the transmitter or the exchange. Hence, maximum power transfer on a bunched pair does not exist, and this severely affects ADSL. There is so much loss when the pairs are bunched, but for voice, no problem. It works well. Technicians must not bunch pairs, especially if the line is to be used for ADSL. Another channel impairment is called skin effect. This is coming from the English meaning of the word skin, and this happens at high frequencies. And we know that ADSL frequencies are higher than voice frequencies. So at distance beyond 5.5 kilometers, voice works well, but ADSL does not. So this is due to this aspect called skin effect, and let's now discuss it. So we are saying at high frequencies or at ADSL frequencies, the magnetic field within a wire forces all charge away from the center of the wire to flow into the surface of the wire, and this leaves the center of the wire useless as a conductor or as a medium. This is called skin effect, and what this means is the resistance of the wire increases at high frequencies. Why? Because we have reduced the surface area through which our current is flowing through. So please take note that at DC and also at low frequencies, the way how a wire conducts is proportional to the diameter squared. And this means that heavy wire does have much better conductivity than thin wire. But at the rate of frequencies or at high frequencies, the conductivity of a wire is proportional to the area, and the advantage of the wire is less pronounced. The advantage of heavier wire at high frequencies or at RF frequencies is less pronounced. What this means is the larger conductors, they begin to suffer from skin effect at high frequencies. Why this happens is because its central core is further away from the skin or is further away from the outer material of the conductor. Please take note that, as I said, this does not affect the voice. It will be clear in the next slide where there is a diagrammatic illustration. But the summary is the conducting surface area of a conductor or of a UTP is reduced at high frequencies, and this increases the resistance. More on skin depth, and we've got an illustration there. The top diagram shows us from this point to this point. That's what we mean by skin depth.
this is where our current will be flowing. This is where and no current, as you can see, is flowing at the center. This is our current density. And we are saying when our current density is dropped from 100% to 38%, then we say that is skin depth. So you can see that as we proceed towards the center, there is no current flowing. Current flowing is 0%. Current density, it increases as we move from the center towards the surface, meaning most current flows towards the surface. So this whole center will not carry any current. Thus we've reduced the cross-sectional area, implying that we've increased the resistance of our UTP line. So we are saying, although the current density under skin effect drops off exponentially from the surface towards this center, this is the same as if a uniform current density were confined to this surface of thickness D. So we are saying the current is 38%, which is the 38% of its full value at skin depth. At this depth, is 38% of its full value at this depth. So we are saying, how do we find skin depth? How is it calculated for copper conductors? Skin depth is equal to 6.6 divided by the square root of F. So this is skin depth in centimeters and F in hertz. Meaning that if we increase this F, we are reducing this skin depth. Take note.
The last but not the least type of ADSO impairment or ADSO fault is called corroded and loose joints. Corroded, which means that we've got some rust, and this rust is going to increase the resistance on a particular joint. Loose joint, I think you know what this means. There is no tightness on the particular joint, and this means that the joint has got high resistance. In other words, it's a loose or a dry joint, and according to me, this is an enemy of ADSL. You find voice working very well, but ADSL won't come up. It goes up and down, and this causes the line to be unbalanced. Let's go through the slide to see what actually happens when we have got corroded and loose joints. It can also be called high resistance joints, and guys, you know, a resistance impedes the flow of current in a particular circuit. Current must flow from the exchange to the subscribers, the premises, and back to the exchange. If the line in the two wires is not the same, we say the line is unbalanced. So we are saying this is one of the biggest network impairments for digital systems, and it normally occurs in a single leg of a pair of wires. This means that if it occurs in a single leg of a pair, it means that the current from the exchange won't be equal to the current going back into the exchange. So we are saying this is caused by either mechanical breakdown or water ingress into a joint, or corrosion of the particular joint over a time. Normally this is what happens. Let's say a customer has had telephone service for a long time, and he or she now wants to be connected onto the ADSL network. If you proceed to the customer's premises and install the modem, you find that the link might not come up while the phone will be working perfectly. The main reason of this is this guy called corroded and loose joints, or the high resistance joints. You need to find these points, and you can do that using a time domain reflectometer. You can locate these points of high resistance, and you redo the joint. So we are saying the effect of a high resistance joint on a single leg of a pair of wires causes the line to become unbalanced, and this allows external noise onto the local loop. One characteristic that you find on a UTP line with corroded and loose joints is if you hear on your telephone receiver a crackling sound in voice, know that the line has got corroded and loose joints. The sound on a particular line, it's a sound that there is an enemy of ADSL on that particular line. Then, so there are some joints that must be redone. And in digital systems, it results in a high bit error rate. This is high bit error rate. So guys, this is an enemy of ADSL. I've worked on a number of lines with this fault. I'm going to show you in the next slide the best tool that when you're working on an ADSL network you must have. This is a must-have equipment. Right, we have mentioned ADSL impairments or ADSL faults. We now want to look at how to test for those faults or the best equipment, which I found to be very important, which is a must-have device when working on ADSL faults. This is called 990 DSL, stands for Digital Subscriber Line Copper Pro Loop Tester. Loop is our line. So this is what it looks like. As you can see, we've got what port stands for plain old telephone system. This is a telephone system for voice. And as you can see, it's written ADSL auto test, TDR auto test. TDR stands for time domain reflectometer. This is a meter that is able to test for short circuit high resistance joints. It picks these so easy so that your life as a technician becomes very easy. This equipment can measure distance to faults. It can, even if there is moisture ingress in your cable, it is able to pick. It is able to pick a disconnection. It is able to pick even when there is an external battery in your cable. It is able to pick even when the line becomes unbalanced. It is very, very good at that, such that you can easily conclude that there is a high resistance or a corroded joints somewhere, somehow. So guys, I found this very handy. It has got also, it can also function as a Batansk, because you can use this to phone. So I found it very, very handy, but you need to calibrate it for it to work. You need to configure the right unit, meters, etc., etc. So guys, I'm saying it is a device that is used to precisely locate common faults on subscriber line, and it verifies the ability of our UTP line to transport various classes of high-speed data service. So guys, this is a must-have a technician working on an ADSL network. It's a must-have. It is able to pick up the DSLAM. Let's say you go on a distribution point and you want to pick where the faults are coming from, the outdoor wire or from the direction of the exchange. It is able to pick the DSLAM and will display losses from the exchange to the distribution point or to wherever you are measuring from. It is also to pick a modem. It is also able to detect a modem. You can go on to you can go on the MDF, and if you disconnect the DSLAM, you can pick a modem connected at the subscriber end, even with the amount of losses. So this is a must-have testing device for digital subscriber lines. Guys, we've come to the end of our video presentations on HDSL technology, and I hope that you have learned something